right? Especially during the service stage, right? Okay, so we have to consider the K value, okay, for that apa ni design process, right? So we have to multiply okay the value of P naught with K, right? So apa yang apa from the video that I've shared with you yesterday, okay, which is with regards to the pre-stress loss, okay, so that is particularly okay for the pre-stress force value, right? So maksudnya value tu bukannya pre-stress force plus pre-stress loss value, right? So the value is not just put there, okay. However, okay, we have apa ni calculated okay, the values in consideration okay, of the immediate pre-stress loss okay, as well as the time dependent pre-stress losses, okay, right? So I believe everyone okay, has already look through the video, right? So video tu apa ni nanti untuk formative assessment okay, for that particular topic, right? So nanti saya akan bagi hari ni lah okay, together with the deflection punya formative assessment, okay. Right, so these are the lesson outcomes okay, for today's topic, right? So at the end of this lesson, you should be able to understand the types of deflection okay, considered in the pre-stress design, then able to calculate okay, the value of deflection and check with the limit state limits okay, stated in the Eurocode 2, right? Okay, so kita ada dia punya certain values, okay. So macam sama juga macam RC design, okay, whereas we have the deflection control. So similarly, okay, for the pre-stress concrete design, okay, we also have the limit scale that we have to check with, okay, right? So only that the method will be slightly different, okay, right? So deflection in a pre-stress member, okay, must be checked since the span over effective depth ratios are not specified in the code, right? Okay, so kalau dalam RC design we have L over D allowable, right? Okay, so however when we talk about apa deflection in pre-stress member, right? So we have to calculate the value of the deflection in particular, right? So maksudnya banyak mana dia deflect, right? So how much is the deformation in our beam, okay, that we have to cater, okay, inside our beam. Right, so deflection considered are due to the eccentric pre-stress force, okay, as well as the normal, permanent, and variable load on the member, right? So the pre-stress force okay, is the P naught value, okay, which we know that when we talk about pre-stress concrete member, okay, we are going to have the induced pre-stress force, right? So yang mana kita push up, okay, our uh, uh, pre-stress concrete beam, right? Okay, so we are going to have that, okay, as well as the value of the eccentricity, right? So eccentricity ni adalah dia punya the location, okay, right? So just to recap back, pasal korang dah cuti kan, dah balik kampung, dah mengundi lah apa semua, right? So takut nanti dah lupa, right? So saya sebut je balik, right? So as for the eccentricity, it's actually the location of the pre-stress force, right? Okay, then we have normal, permanent variable load on and variable load on the member. So this is basically kita punya UDL lah, right? Apa load yang ada dekat atas kita punya beam, right? So sometimes we have UDL, okay. So ada juga at times we are going to have point loads as well, okay, right? So yang ni adalah loadings yang we are going to consider, okay, in order to calculate the deflection, right? Okay, so this is one example, okay, which is showing us the deformation of a statically determinate member, right? Okay, so whereas we can see that the first figure, right, which is figure A, okay, so this is the original geometry, okay, whereas we have the supports, okay, then we also have the loads, okay, which is acting on the beam, right? So when this loads is subjected to the beam, what happens to the beam is that it will have the tendency to deflect, right? Okay, so this is figure B, right? Okay, whereas we can see that we have the deformed shape. So whenever we mention about deflection, so it means that basically we are going to calculate this value, right? So tengok dekat throughout the beam, okay, dekat mana yang dia akan deflect, right? Kat mana dia akan bengkok. So which one will give us the maximum value, right? Okay, so this is where we can see that this is the deformed shape. Okay, right? So benda tu yang kita nak calculate. Okay, so for the member design, okay, as an uncracked section under full load, okay, whereas we have FCT less or equals to FCTM. right? Okay, so this is in terms of dia punya tensile stress, okay, in the beam itself, right? Okay, so if we are designing for a member, okay, under uncracked section, okay, therefore we are going to do the simple linear elastic analysis based on the gross concrete section. Okay, it is sufficient for reasonable and realistic estimate of deflections, right? So yang ni kalau kita design kita punya section tu as an uncracked section, right? So, but for members, okay, that is designed as cracked sections, okay, whereas kita punya value of FCT exceeds FCTM, right? So it means that the tensile stresses is much higher. Therefore, it is necessary to base the deflection calculation on cracked section with the reference to the code, right? Okay, so kita akan ada additional requirements, okay, that we have to look into when we are designing the member as a cracked section. Okay, right. So kita tengok yang ni untuk uncracked section. Okay, the concrete is assumed to be linear elastic in both tension and also compression, right? So when we have a beam, right, so therefore we are going to have these two zones, right? So the tension zone and also the compression zone. So for both zones, okay, we are going to consider both are in linear elastic, right? So together with the non-prestressed reinforcements as well as the prestressing tendons, right? So bila kita consider, then kita akan consider both reinforcements as well. So it transforms the bonded reinforcement into equivalent areas of concrete and performing elastic analysis. Thus, okay, we will be assuming, okay, that the concrete can carry the imposed stresses, okay, which are from the compressive and also tensile stresses. Okay, right. So as for the crack section, right, so yang ni pula untuk crack section, yang tadi kita ada FCT is more than FCTM. After cracking, the internal actions can only be taken by the steel reinforcement. So this is basically we are back to the RC punya principles, right? So kalau RC punya principle tu basically the concrete will not be taking the tensile forces or the tensile stresses. Okay, but instead, okay, the steel reinforcement will be taking the tensile stresses, okay, in the section. So internal actions can only be taken by the steel reinforcement, okay, and tendons, and the uncracked part of the concrete section, right? So yang ni after cracking lah. So bila dia dah start crack, okay, then steel reinforcement will take its role, okay. So barulah dia akan function, right? So assumptions that is made in crack section analysis, okay, is that the plane section remains plane. So yang ni sama juga macam RC design. Okay, then perfect bond, okay, between steel reinforcements or tendons and the concrete, right? So yang ni kita assume, right? So walaupun sebenarnya kita tak tahu kalau dalam structure, okay, after it has already been cast, right? Okay, so kita pun tak tahu whether we do have the perfect bonding or not, right? So however, in the design process, okay, when we calculate for the crack section, so we are going to assume that we have the perfect bond. Okay, then we have tensile stress in concrete is ignored, okay, whereas the concrete tensile does not contribute to the cross-sectional properties. Right, so the material behavior is linear elastic. So in concrete, non-prestressed and prestressed reinforcements, right? So kalau kita tengok in terms of the crack section, so basically we are back to the RC concept, right? Okay, whereas the steel reinforcements will take the tensile forces, okay, and as for the concrete, okay, it will not contribute to any tensile strength, okay, right? So yang tu is basically dia punya basis lah, okay, on the uncracked and also cracked sections. Okay, right. So now we are going to look into the basic requirements of deflections, right? So our topic today, okay, is basically we'll be focusing on the deflections, okay. So similar to reinforced concrete requirements, deflection under the action of quasi-permanent load, okay, should be less or equals to span over 250, okay, measured below the level of the supports, right? Okay, so we have this limitation, right? So dia kata, so we have to calculate, later nanti kita akan calculate, okay, that our deflection should not be more than this value, right? So kita tengok kita punya span length tu berapa. So for example, if we are designing for a 30 meter span beam, right? Okay, so therefore we are going to calculate 30 meters, okay, divided by 250. Right? Okay, so our deflection value, okay, under the action of course permanent loads must be lesser than this. Okay, then we have another limit, okay, which is span over 500. Okay, whereas the maximum movement, okay, is calculated, right? So susceptible to damage by movement, right? Okay, so we are going to check with this limit as well, right? Okay, which is span over 500. Right. Okay. So in terms of the calculation, right? So we are going to have the deflection as well. That is due to the pre-stress loading, right? So pasal kita ada pre-stress, so therefore we have the pre-stressing force as well as the eccentricity. So we need to calculate that as well in order to calculate the value of deflection, right? Okay, so tengok kat sini we have the deflection formula, right? So deflection that is due to the pre-stress loading. Okay, so basically we are going to calculate, okay, using the P and also the eccentricity value, right, over the length of the member. So what we can see here, okay, so this is one example that is for, this is the equation, okay, that we are going to use for the straight tendon profile, okay. Whereas as for this equation, okay, so we have P, okay, which is our pre-stressing force, and also we have E, okay, which is the eccentricity. So this is not benda yang dia panggil yang actual uh, uh, stress, okay, yang dia duduk betul-betul dekat apa ni neutral axis, right? So however for this one, okay, we are going to have the eccentricity, right? So in view of this, okay, so therefore it is going to induce the moment, right? Okay, so if you still remember dalam structural analysis code, right? So we can derive the equation actually, okay, bila kita ada moment, okay, then we can actually derive the value, okay, or the equation for the deflection, right? So kita boleh calculate juga dekat S2 dia punya deformation. Okay, right. So maximum midspan deflection. Okay, then the equation is the moment, okay, multiply with L square over 8EI. Right. So this is the equation, okay, in consideration of the moment. Right. So however, since in this case, right, okay, so we have the pre-stress force, okay, and also we have the eccentricity. So PE will be the value of moment, right? So kita akan masukkan yang ni into the equation, right? So that is why we are going to have y equals to PEL square over 8EI, right? Okay, and for if the E value is positive, okay, therefore the deflection that will be considered here is negative, right? Okay, so especially when we are talking about the beam, okay, that is subjected to the pre-stress force, and it is at transfer stage, right? So bila dia dekat transfer stage, okay, then we know that it is only subjected to the self weight, okay, of the beam itself, as well as the pre-stress force and also the eccentricity. So usually, okay, at this stage we are going to have our beam that deflects upwards, right? So they deflect upwards. Jadi kita punya this is not under service loads yet, right? So kita tak letak lagi loading dekat atas tu untuk kita punya beam, right? Okay, so this is the equation for a straight tendon profile. Okay, then we also have another case, okay, whereas we have the parabolic tendon profile, right? So kalau tengok dekat sini for the straight tendon profile, so you can see that the tendon that we have here is in red color. Right, so yang color merah ni, right, so kita boleh tengok bila dia sebut straight tendon profile, dia sama. Dia punya eccentricity from end to end. Right, okay, however, we have another case which is the parabolic tendon profile. Okay, whereas you can see here, right, so this is the tendon. Okay, then this tendon, okay, will have a different eccentricity between the ends and also the midspan, right? So as for this example, okay, at the ends, the eccentricity is equal to 0, right? So dia kosong, dia duduk betul-betul on the neutral axis. However, in the middle, we are going to have the value of EC, right? So this is the eccentricity at the center of the beam, right? So value dia adalah berbeza. Okay, right. So in view of this, okay, when we calculate, okay, the equation for the value of loads, okay, that is subjected to this prestress force as well as the eccentricity, okay, will be like this, right? So moment is equals to PEX, right? So PEX ni maksudnya throughout EX tu maksudnya throughout our beam, right? Okay, so berapa dia punya value? So this value will actually change, okay, with the location of this eccentricity, right? So dia start dengan kosong, dia punya eccentricity at the ends, okay, then towards the center, then we are going to have the maximum eccentricity. Okay, right. So in relation to UDL, okay, of a simply supported beam, right, we can actually rearrange the equation for moment, right? So dia akan jadi macam ni lah, right? So if we rearrange this equation, okay, for moment, so moment basically adalah WL squared over 2, right? So due to the eccentricity, so if we rearrange the equation, so we are going to get this, right? Okay, so WE is equals to negative, okay, 8PEC, right? So which is the eccentricity at the center, okay, divided by L square, right? Okay, so this is what we are going to combine, okay, with the mid-span deflection that is due to UDL, right? So yang ni UDL yang dekat atas beam lah. Maksudnya basically, kalau kata kita ada simply supported beam, then we are going to have the external UDL. So loading dia dekat atas tu. So kalau kata at transfer, then we are going to consider this UDL as the self weight. Okay, however, kalau kata kita consider untuk service, okay, then it is going to have the service loads and the self weight of the beam itself as well. Okay, right. So therefore, okay, the deflection that is due to WE, right. So yang ni tadi adalah due to UDL. Okay, so this is one. And this is another one, okay, which is the deflections that is due to the pre-stress force, right? So we have negative 5/48, right? So multiply with PEC times with L square over EI, right? So no need to worry, okay, if the question appears in your exam, okay, in your test, okay, then these equations will be given to you, right? Only that you need to have the ability to choose which equation is more suitable for your question, right? Okay, well, for your answer, for your question, tak for your answer kan, right? So you have to choose. However, the equations will be given to you, right? So kita tak adalah suruh you derive the formula, right? So kita akan bagi directly, cuma you kena pilih lah equation mana yang bersesuaian untuk guna dalam calculation, okay? Right, so kalau untuk parabolic tandem profile, so basically we are going to have two values, right? So we are going to have one that is due to the UDL and another one is due to the pre-stress force, right? So itu yang dalam equation dia ada PE, right? So the difference between these two equations, equation yang atas ni ada W je, right? Okay, tapi equation yang bawah ni dia akan consider the pre-stress force as well as the pre-stress punya eccentricity, right? So itu dia punya difference. Then we are going to combine both equations together, right? Okay, boleh follow saya setakat ni?
Boleh, madam.
Ke dah lena dah sambil-sambil pegang telefon tu ke kan? Menengok saya bagi lecture.
Astagfirullahalazim.
Astagfirullahaladzim, siapalah tu kan? Okay, right. So next, okay. So tadi tu adalah satu parabolic tandem profile yang mana dekat hujung dia eccentricity is equals to 0. Okay, so this is another one whereas we do not have a zero eccentricity at the ends. Right. So tengok kat sini. Okay, we are going to have a value of eccentricity as well at the ends of our beam. Right. So hujung tu pun ada eccentricity. It is not directly on top of the neutral axis. Okay. However, we have the value of eccentricity at the end. Okay. And therefore, we are going to have another value of EC. Right. So EC ni adalah dia punya mid eccentricity. But it is not measured, okay, from the location to until the neutral axis. Tapi dia kena sampai kepada the value of the eccentricity that is on top, right? So kat sini kita akan ada E0 and also we have E prime C. Right, okay, so here the equation will be macam mana nak kata, altered, right? Okay, in order to consider this extra eccentricity, right? So dia ada extra lah pasal kita ada eccentricity at the end span. So we can see that here, okay, we are going to have two equations, right? So kalau kita tengok yang tadi parabolic ni, ada satu sahaja equation, okay, yang mana considering the PE value. Okay, however, if we do have eccentricity at the ends as well, so therefore, the calculation for the mid-span deflection will have to also consider the E naught value, right? So E naught ni adalah E naught at the end span, kat hujung, right? Then we have E prime C. So E prime C is the center punya eccentricity, right? Okay, so only that dia punya center E tu dia bukan up to the neutral axis, but it is up to the E naught value. Okay, right. So we have to calculate this. Okay, so the equation will be two equations. Okay, so one is considering PE naught KL square over 8EI. Okay, and then another one is minus with K5 over 48, right? PE prime C, right? L square over EI, right? So we are going to consider another two values, right? So kita ada dua. Kalau macam yang tadi ni, kita calculate ni je. 5 over 48 ni, right? So however, for this one, we are going to have this extra portion, right? Which we have to consider the ends of our beam, okay? Right, so for more complex tandem profiles, conveniently estimated on the basis of coefficients, it can be evaluated for common arrangements, right? So the deflection is on the basis of y equals to KL square, K over EI, okay, whereas K is the variations of the curvature due to the pre-stress along the member length, right? So basically yang ni adalah dia punya basis lah. Okay, kenapa kita guna PE naught L square over 8EI, right? So if you want to find the derivation, okay, for this formula, so you boleh refer kepada textbook yang Mosley, right? So Mosley yang Eurocode 2 Eurocode 2 lah, right? Okay, so Mosley ni dia buku design untuk reinforced concrete design, right? So you can refer to this textbook, right? Okay, so kalau nak tengok dia punya derivation lah, macam mana this equation is derived, right? Okay, so again, no need to worry, right? So this equation will also be given to you, okay, during your exams, right? Okay. So three principal stages, okay, that whereas deflection may be critical and needs to be assessed, right? So there are certain, dia bukannya kita calculate sekali sahaja, right? Okay, however, we have certain stages, okay, in the process of construction, okay, of a prestressed concrete beam, okay, whereas we have to check for deflection, right? So the first stage is at transfer, okay, a check of actual deflection at transfer for comparison with estimated values, right? Okay, so it is a useful guide, okay, to show that the pre-stressed beam has been correctly constructed, right? So yang ni first one, right? So at transfer, awal-awal tu kita kena check dah dia punya value of deflection. Then the second one is under dead load, okay, before the application of finishes, okay, which is to permit subsequent movement and possible damage to be estimated, right? So this is the second stage. Then the last one is long-term under full quasi-permanent actions, right? So this is basically bila kita sebut long-term, it is already under service loads, okay? So it is to determine the subsequent movement, okay, and also to assess the appearance of the final structure, right? So this is under service. Bila kita dah apply all the loads, okay, on top, okay, then we are going to consider the full quasi-permanent action, and we are going to assess, okay, the value of deflection again, right? Okay, so these are the three principal stages that we are going to consider, right? Okay, so for the these deflections, right? So we are going to have the short-term deflection, okay, and also the long-term deflections, right? Okay, so for short-term deflections, okay, it is basically based on the material properties associated with the characteristic strength and with actual loadings, right? So usually as for this, we are going to consider the factor of safety of 1, right? Okay, and deflection also falls under serviceability limit state. Okay, it is not under ultimate limit state. Pasal deflection ni is basically related to the comfort, okay, of the occupants, right? So kita tak nak, we do not want our structure to deflect too much, okay, until it affected the function of the structure. Alright, so kalau kata dia deflect too much, kita pun tak selesa dah nak duduk dekat situ. Ataupun it could cause failure, okay, to the brick walls, okay, to the partitions, right, due to the deflection, even though the structure has not failed yet, right? So deflection dia excessive deflections, okay, kadang-kadang dia boleh jadi excessive deflection. However, it could only affect, okay, the appearance, okay, of the structure, right? Okay, however, it is still a safe structure, right? So masih selamat lah nak guna, tapi bila dia deflect too much, then we are going to see crackings, okay, and also failures, right? So therefore, it is not comfortable for the user, right? Okay, so pasal tu kita kena check for deflection. And that is why deflection falls under serviceability limit state. Okay, dia bukan under ultimate. Okay, right. So for long-term deflections, okay, not only taking into account the pre-stress loss, okay, but also we have to consider the effects of creep, right? Okay, so effects of creep, okay, on the applied loading and the pre-stress loading components of the deflections. Okay, so when we talk about creep, okay, basically this is another type of deformation, right? Okay, dia bukan failure, tapi it is another type of deformation. Okay, whereas when we have our structure, okay, that is subjected to loadings for a long term, right? So dia tempoh masa dia panjang. Jadi we are talking about creep, we are talking about concrete, right? Okay, so concrete will be subjected to creep, okay, as time goes by, right? So maksudnya loading tu sentiasa ada kat situ, loading dia sama, tapi the loading is sustained at the same location for a long time, right? So bila dia sustain for a long time, so what happens to the concrete is that it has the possibility of cracking, right? So pasal dia pegang loading tu lama, so biasanya dia akan ada macam minor cracks, right? Then we are going to have deflections, okay, in the structure and so on. That is due to the effect of creep, right? So slowly, so pasal tu lah nama dia creep, pasal it happens slowly, right? So dia punya cracking tu is very small cracks, okay, however it will be increasing a long time, right? Okay, so this is when we are dealing with concrete, right? So this has to be considered in the deflection calculation as well, right? So creep increases deflections, right? Okay, whereas we are going to consider the creep coefficient, okay, in the deflection calculation, right? So kalau tengok dekat sini, we have the modulus of elasticity, okay, effective modulus of elasticity. Kalau tengok equation ni, right? Okay, so effective modulus of elasticity is equals to ECM, right? So this is the modulus of elasticity for concrete divided by 1 plus with the creep coefficient, right? Okay, so creep coefficient ni basically you have already learned previously in your RC design, right? Okay, so yang dekat dalam kita punya level, you are just going to apply the value, right? Okay, so creep coefficient. Okay, so this is the table we can see from figure 3.1, right? So the creep coefficient can be determined based on this, which this value is depending on the aggregate properties, okay, the mixed design, the curing conditions, okay, the age of concrete at first loading, duration of the load, okay, as well as the section dimensions, right? So kalau kita zoom in ni, right, so basically kita akan tengok semualah, right? Okay, kita tengok berapa dia punya grade of concrete, right? So this is for the grade of concrete. Okay, then we are going to look into the height of our structure, okay, dimension of our structure. So what else yang ada dekat sini, right? Okay, so kita ada dua cases dekat sini. Okay, so one is for inside conditions. Okay, so yang ni daripada Eurocode, dia punya figure ni, right? Okay, so and also we have for outside conditions, right? Okay, so kita akan tengok satu-satu ni, apa dia punya size, okay, and also what is the grade of concrete. Okay, then we are going to find the creep coefficient from this apa figure, right? So creep coefficient tu yang ni, right? So basically kita akan buat macam ni lah, right? So we have this method, right? So we have number 1, number 2, number 3. Dia tunjuk lah nak tengok yang mana dulu, okay, in order to get the value of the creep coefficient. Okay, right. So yang ni boleh tengok balik lah kot. Basically saya, kalau tak silap saya, dalam RC design ada ajar macam mana nak calculate the creep coefficient. Okay. Right. So kalau kata ada yang interested, okay, to know on how to determine, right, then you can come to me lah. Right. So nanti saya akan tunjuk macam mana dapatkan dia punya value. Okay, in accordance to this figure. Okay. Tapi for the moment untuk your stage, right, so you will have apa ni, saya rasa kalau untuk mini project kena determine juga kot. Okay, tapi kalau untuk test, okay, then the creep coefficient will be given to you. Okay, right. So let's see the example, right? Okay, so dia kalau cerita-cerita ni, dia tak nampakkan macam mana nak apply, right? So now we are going to look into the example. Right, so estimate the transfer and long-term deflections for 200 times 300 millimeters beam of 10 meters span. Okay, the pre-stressing tendon has a parabolic profile with mid-span eccentricity of 50 mm and with zero eccentricity at both ends. Right, okay, so yang ni basically kita gunakan example, okay, yang kita dah solve previously. Right, okay, so I have already shown you that we have used the Magnell diagram. Right, okay, and we have already determined, okay, the value of the initial pre-stress force, okay, which we have decided to take 700 kilonewton. Right, okay, then untuk in terms of dia punya profile, right, so we have chosen a parabolic profile, okay, with the mid-span eccentricity of 50 mm. Right, so yang ni pun daripada previous example yang kita buat dia punya cable zone profile. Okay, so with zero eccentricity at both ends, right? Okay, so kita akan guna equation yang tak ada eccentricity dekat hujung lah. Okay, so P naught is 700 kilonewton, okay, considering the pre-stress loss of 20%, right? So imposed load is 2 kilonewton per meter square, variable load is 1 kilonewton per meter square. Okay, the modulus of elasticity is 35, okay, creep factor, okay, given here directly is 2. Okay, right. So kita tengok dia punya solution. Okay, so what we are going to calculate first, okay, is the self-weight of the structure. Alright, so self-weight is equals to 0.2 times with 0.35. Right, so since we are considering the apa ni nak kata, a rectangular section, right? So example yang saya bagi ni cuma untuk rectangular section sahaja, right? So 1.75 kilonewton per meter. Okay, then we can calculate the value I, which is the upper moment of inertia. So we have 715 times with 10 to the power of 6 millimeter to the power of 4. Okay, so first that the value of deflection that we are going to calculate here, okay, is the value of deflection at transfer. Right, so yang ni first stage. Okay, kita tengok dulu at transfer, whereas we are going to consider W minimum. Right, so W minimum ni maksudnya kita akan just consider the self weight value. Right, so yang ni first equation. Kalau we go back, okay, to the equations that we have just now. Okay, so we are referring to a parabolic tendon profile. Okay, whereas dia punya E naught value, okay, is equals to 0. Right, at the ends, end span, right, dekat ujung dia tu, at the ends of our beam. Right, then dekat tengah tu kita ada EC lah. Right, okay, so therefore as for this equation, okay, for a parabolic tendon profile, we are going to combine these two equations together, right? So kita ada equation 1 and also equation 2. Apa besar sangat ni? Okay, right? So equation 1, okay, and also equation 2, right? So kita akan combine dua ni. Okay, kita akan tambah these two equations together, right? Okay, so we have y equals to 5 kWL to the power of 4, okay, over 384 EI, okay, and also 5 over 48, right? So combine these two equations, okay, to calculate the value of the deflection at transfer. Okay, right. So masukkan dia punya value kat sini. So ECM, okay, which is the modulus of elasticity, is also given the question. Okay, then kita akan masukkan juga P0. Right? So P0 is 700. Okay, we have already decided previously from the Magnell diagram. Okay, then we also have EC, right? So EC is the eccentricity at midspan, right? So yang dekat hujung tadi tu adalah kosong, right? So masukkan yang tu. So substitute all the other values, okay, the ECM value and also I. So what we are going to get here is negative 5.46, right? And we see that we have a negative value here, right? So this negative value means that, okay, we are going to have a negative deflection. So positive deflection, dia deflect ke bawah. Tapi kalau negative deflection means that we have our beam that is bending upwards. Okay, pasal tu dia punya deflection dia adalah negative. Right, so yang ni adalah negative. Okay, right, so yang tu at transfer. Okay, then the second one is at the application of finishes. Right, so yang ni kita nak consider the loads, the deflection that is only due to the weight of finishes. Yang tadi tu at transfer, we only consider the value of the self weight of the beam, right? So beam, prestressed beam kita tu sahaja without any finishes. Okay, so now we are going to consider, okay, the extra deflection, okay, that might be due to the weight of finishes, right? So in order to do this, kita akan consider this weight of finishes as UDL. Okay, macam UDL jugalah. Maksudnya kita ada kita punya beam, right? Then kita ada finishes dekat atas, right? So yang ni akan jadi UDL. So as for the equation, we are going to use this equation, right? So equation of deflection that is due to UDL, right? So kita tambah. Jadi the difference here is only in the value of the finishes, right? So kita masukkan value of finishes to into this equation, right? So masukkan dekat W. So substitute all other values and we are going to get 10.41, right? So dapat 10.41. So we plus this value, okay, with the deflection that we have already determined just now, which is negative 5.46. Okay, value yang atas ni. Jadi kita combine, therefore we are going to have positive 4.95 downwards. Right? Okay, so kita ada extra lah. Pasal kita ada dia punya weight of finishes. Okay, so therefore we are going to have extra deflection. Okay, so calculate yang tu. Then the next one is in long term, okay, due to the quasi-permanent action, okay, due plus the pre-stress force after losses. So basically, bila kita sebut in long term, okay, means that now we are going to consider the service load, right? Okay, so it is no longer in the transfer stage, okay, but now we are going to consider the service load as well. Okay, right. So assuming 30% of the variable load contributes to the quasi-permanent action, right? So if you still remember previously, kita dah belajar dah macam mana nak calculate quasi-permanent action. Okay, so it is equals to GK plus with phi times with QK, right? Okay, so phi ni kita ambil 0.3 lah. Okay, which is from the table, okay, table apa A.1 kot yang previously kita dah tengok, right, in order to calculate the quasi-permanent action. So boleh tengok balik daripada previous example. So dia punya calculation dia adalah self weight, okay, plus with finishes. So this is GK, right? So yang ni, this part is GK, right? Then this part is the QK part, right? Okay, whereas we have this phi value here, right? So kita masukkan, multiply, okay, then we are going to get the quasi-permanent action value of 4.05 kilonewton per meter, right? And then as for the pre-stress loss, pre-stress forces after losses is 0.8 times with P0, right? So kita boleh calculate dekat sini, pasal kita punya P0 is 700, okay, therefore we can use here 560 kilonewton. Okay. Right, so calculate yang ni, right? So this is basically in order to calculate the quasi-permanent action, right? Okay, then the next part is to calculate the value of deflection, right? Okay, so tadi dah calculate. So untuk deflection, okay, we are going to consider the creep coefficient as well. Right, okay, so tengok dekat sini we are going to have modulus of elasticity, okay, the effective modulus of elasticity under creep, right, okay, so therefore we are going to have ECM, okay, divided by 1 plus with the creep coefficient. So dalam question ni, okay, we have our creep coefficient of 2, right, so 35 divided by 1 plus with 2. Right, okay, so now the effective modulus of elasticity has become 11.7 kilonewton per millimeter square. Right, so in consideration of the creep coefficient. Right, so then kita calculate dapatkan dia punya deflection value. Okay, that is due to the creep. Right, okay, so dekat sini kita ada 5 over 384. Right, okay, so this is the value, okay, of deflection, okay, that is due to the quasi-permanent action, right? So you can see that we have this value here, okay, which is 4.05. So 4.05 ni dapat mana? It is from this value, right? So tadi kita dah calculate dia punya quasi-permanent action. So this is 4.05 untuk kita masukkan dalam calculation. Okay, then the next one, so this is due to UDL. Okay, so yang ni yang UDL lah, which is the quasi-permanent action. Okay, then yang next one ni pula, dia adalah due to PE. Right, okay, and as for the PE value, right, so this is E. Okay, for the P value, we are going to consider the value of the pre-stress force after losses. Okay, so maksudnya kita ambil 560 kilonewton. Okay, pasal dah tolak dah that 20%. Right, so substitute that into the equation. Right, so we see that we have P and also we have E here. Right, so the other values, okay, pasal kita consider creep. Okay, so therefore the EC value will also change. Right, so tengok dekat sini, this is the EC value. So instead of using 35, so now we are using 11.7 kilonewton per millimeter square. Right, so ada perubahan dekat situ. Kita tak pakai value yang sama. Okay, so after we have already calculated that, okay, then we are going to get our value of deflection that is in the long term, okay, is 28.17. Right, so bila 28.17, okay, the value is positive, therefore, okay, it is considered as moving downwards. Right, so kita boleh daripada sini, so this is at service. Okay, saya nak tulis kat sini. At service. Okay, so bila at service, okay, then we are going to compare, okay, with the deflection limit. Okay, right, so compare dengan dia punya deflection limit, which has to be less or equals to span over 250. Right, okay, so untuk question ni, dia punya span length dia is 10 meters. Right, okay, so therefore kita masukkanlah. So 10 meters, okay, so divided by 250. So 10 meters is 10,000 lah. Okay, siapa pula telefon ni? Kejap Hello. Hello. Yeah, morning. Yeah, Hazrina. Aha. Ya, pasal semalam I dah cakap dengan Miss Jun. Lepas tu I kata dengan Miss Okay. Sorry. Ada pula orang telefon kan. Sekejap Tadi kat mana? Lupa dah saya pun orang telefon. Okay. Right. So kat sini deflection limit. Right. Okay. So deflection limit dia adalah 10,000 divided by 250. So we have 40 mm. Right. Okay. So dia punya limit. So kita compare dengan value that we get. So our value is 28.17. Right. So 28.17 is less than the limit of 40, right? So therefore it is satisfactory, right? So yang ni kita check only at service load, satu sahaja value yang kita check, right? Okay, so this is where we are considering all the values of deflections, okay, inclusive of the values that is at transfer, right? So yang tadi tu kita ada YB, right? So mana tadi YB, yang ni quasi permanent action, right? So yang ni adalah the value of YB, right, which is at the application of the finishes, right? So dekat sini yang ni value ni adalah at transfer. Okay, yang ni pula adalah at application of finishes. Okay, jadi kita punya finishes, right? So at the end, okay, we are going to have to compare, okay, these two values, okay, with the spend over 500. Okay, right? So kita akan combine, okay, the value of deflection, okay, at service, okay, as well as at the transfer stage, right? So kita ada dekat sini 28.17, okay, which is downwards, and also the value that is 4.95. Okay, so this is after the application of the finishes tadi, right? So kita combine these two, okay, therefore we are going to get here 23.22 millimeters, and we are going to compare with span over 500. Right, so kita tengok kat sini kita punya span is 10 meters, right? So span over 500 is 20 mm, right? So kalau tengok dekat sini bila kita calculate kita dapat 23.22, okay, which is larger than 20, right? So therefore what we can see here, okay, is that kita punya deflection ni is not satisfactory, right? So maksudnya yang tadi tu okay, okay, yang mana kita dah check dengan spend over 250 tak ada masalah. Okay, however, okay, when we check for the total punya value of spend, okay, whereas we are considering dia punya movement, okay, so yang ni adalah limits yang tadi kita dah tengok dekat atas ni. Okay, nanti kan tanya saya dekat mana kita dapat dia punya spend over 250 and 500. Okay, which is this one? Right, so this is actually given by the Eurocode, right? Okay, so kita tengok in terms of the maximum movement, okay, so yang ni yang kita check. Yang tadi tu adalah deflection under the action of quasi-permanent loads, okay? So for the next part, okay, is that we are going to consider for maximum movement, which is span over 500. So bila span over 500, dekat sini dia tak lepas. Jadi what can be done? Okay, if we have these cases whereas the value is not satisfactory, okay, so what can be done, okay, is that we can actually reduce the value of the pre-stress force, right? So bila kita kurangkan value pre-stress force, what happens, okay, is that the value of the deflection will also decrease, right? So dia akan kurang lah. Okay, then the next is to find the new range of eccentricity and select the eccentricity to be used for mid-span, okay, from the Magnell diagram, okay, or we can also recalculate the deflection values, right? Okay, so recalculate maksudnya tengok balik lah kita punya calculation, okay, and then recheck with the EC2 deflection limits, right? Okay, so ini adalah options yang kita boleh buat lah, right? So we can reduce dia punya value, right? So basically untuk kita reduce dia punya value, we are going to go back to the Magnell diagram punya values lah, kita tengok balik, right? So if we look back, okay, for our Magnell diagram, pasal kita guna example yang sama. Sekejap, saya scroll down. Okay, right? So which is this one? Okay, so basically previously kita ambil P naught K equals to 700. Okay, so we have already looked into dia punya portions ni, right? Okay, and also from here, okay, we have already determined the minimum P naught and also maximum P naught, right? Okay, so kita boleh dapatkan dia punya value of the P naught here, right? And also, okay, we can determine the new value of the eccentricity, okay, from this Magnell diagram as well, right? So maksudnya boleh make adjustments lah, right? Then bila kita dah make adjustments, okay, then we are going to redecide on the value of the eccentricity, right? Okay, so kalau katalah macam yang ni, then mungkin kita boleh ambil kita P naught yang tu is 700, okay, yang kita guna tu adalah 700. So mungkin dekat sini boleh kita ambil yang P naught value of 600 for example, right? Okay, so tengok dekat sini, for example, katalah kita ambil P naught value of 600 kilo Newton. Okay, so kita boleh tentukan berapa dia punya E value, right? Okay, so kalau P naught 600, right? So kita kena calculate lah 10 to the power of 6 P naught, right? So P naught is 600, so 10 to the power of 6 over 600. Okay, so value yang nak kena tengok daripada magnet diagram ni berapa? Cuba calculate jap. Berapa dia punya value nak kena tengok daripada magnet diagram? Kalau P naught kita 600, what would be the value? Mana orangnya ni? Ada ke tak ada? Cuba kira jap. Saya seorang ke di dalam dunia CES525 pagi ni? Berapa value dia? Klik-klik je ni. Apa value dia? Nak tengok daripada table, daripada magnet diagram ni. Minggu depan nak test ni. Mana orangnya ni? Berapa value dia? Kalau kita ambil P naught 600. What would be the value that we are going to find from the magnet diagram?
$18.
18?
166.666 madam.
166.66 tu lah kan? So ambil lah 1667 macam tu lah kan? Ataupun 1670 lebih kurang. Right? Okay. So approximately this lah. Okay. Right? So kita akan tengok basically daripada this magnet diagram. Okay. So 1670 ni approximately here. Sekejap. Macam mana saya nak buat bagi dia jadi garisan dia lurus Kalau saya lukis roughly, tak reti pula saya macam mana nak bagi dia garis lurus. Tengok lupa dah saya pun lama tak pakai. Tak apalah. Kita tarik je lah kan. Shapes tu. Okay. Jadi kita tarik dia punya line. So approximately kalau satu, ini 1500, 1600. Approximately here lah kot. Okay. So tarik sampai sini. Okay. Tak lurus pun. Ria saya klik kat situ tadi tapi tak jadi pun. Okay. Okay. Right. So dekat sini then you can drag down lah. Tadi okay je. Okay. Right. So yang daripada sini sama juga. Okay. Kita akan drag down. Macam tu. Okay. Right. So basically dekat sini, okay, kita ada dia punya value tu is approximately 1670 lah. Right. Okay. So and we have the range of eccentricity, okay, in between 60 to 81, approximately macam tu lah, 81, 82. Right. Okay. So katalah dekat sini we change the eccentricity to 70. Right. So katalah kita ambil eccentricity dia 70. So P naught dia adalah 600. Okay, so instead of using 700, so now we change it to 600. Okay, with the value of new eccentricity, okay, of 70 mm. Right? Okay, so kita boleh tukar yang tu. Okay, and we can recalculate, okay, the value of deflection. Okay, pasal kita nak tengok dekat sini dia lepas ke tak. Okay, untuk kita punya value of loads. Right? So loads yang lain tak ada perubahan. Okay, value of deflection, value of loads pula. Value of deflection. Okay, so yang berubah adalah the value of the pre-stress force, right? So kita akan ubah dia punya value of pre-stress force. Okay, right. So boleh tak cuba calculate? Okay, so yang ni kita ambil 600 lah. Right, so try P naught of 600 kilonewton, okay, with the new eccentricity of 70 mm. Okay, pasal yang asal dia, eccentricity dia adalah 50 mm. Right, so try to calculate, right, so tengok dekat sini, sama ada dia lepas tak this reflection limit. Right, okay, so saya bagi dalam 15 minit. Right, so try to calculate. Pakai je yang saya apa yang ada dalam example tu, cuma recalculate sahaja dia punya value. Okay, right? So saya bagi dalam 15 minit, okay, nanti kejap lagi dalam 9.35 macam tu, nanti kita tengok balik jawapan dia. Boleh? Boleh ke?
Boleh.
Dia macam cakap dengan apa ni je kan, macam cakap dengan dinding je kan. Memang kena buat kelas face to face korang ni.
Madam,
kalau
peanut tadi berapa?
macam mana? P-naught
Peanut tadi berapa?
600.
Okay.
E700. 700 pula. E70. Okay, cuba calculate. Nanti kita tengok and compare the answer. Okay. 15 minit lagi nanti kita tengok balik.
Madam, dia tak lepas lah madam.
Tak lepas Dapat apa?
19.16.
19.
YD
YD lah. Ingatlah sekali tu. Kalau 19, limit dia bukan 20 ke? Limit dia 20 kalau 19.
Dia lepas.
Kalau
Dia
19
lepas. Dia tak
lah kan?
boleh lebih daripada limit lah. Lepas.
Lepas
Dia tak
Yang
boleh
lain dapat
lebih
sama
daripada
tak?
20.
Macam mana Hafiz?
Dia kira tak boleh lebih daripada yang limit tu lah. Yang L bagi dengan 20 tu 500.
Ya, betul. Yang lain dapat sama ke? Saya tak boleh nak on camera pula. Salah komputer saya ni. Yang lain dapat sama tak? Dapat sama tak dengan Hafiz? Kira tak? Tak habis kira lagi ke?
Habis lagi madam.
Tak habis lagi. Tapi tadi Hafiz pakai E70 ke 50?
70.
70.
Yang P-Note 600.
Macam mana? Untuk 600 tu lah kan?
Yang madam suruh ganti dulu.
Okay. Right. So yang lain dapat sama tak dengan Hafiz?
Dapat 19 juga, madam.
19 juga. Alright. So maksudnya dekat situ kita boleh tengok yang bila kita make adjustments on dia punya value of sekejap saya share screen. Bila kita ubah dia punya value, right? So that is one of the options lah yang kita boleh buat. Right? Whereas we change the value of the pre-stress force. Right, so kita change dia punya value tadi daripada kalau macam dekat sini value dia asal dia adalah 700, so we change this to 600 tadi kan. Lepas tu kita bila kita ubah kita punya value of the P0, right, then we have to change dia punya value of the eccentricity as well lah. So basically dia punya design tu kita akan go back to the kita akan go back kepada kita punya Magna diagram, right? So because the Magna diagram tu adalah kita punya basis untuk kita pilih the value of the pre-stress force as well as the value of the eccentricity. So bila kita dah go sampai kepada deflection, tapi kita punya selection of the pre-stress force and also eccentricity is not suitable, then we have to go back to kita punya design balik lah. Right, so that we can make adjustment on the value of the pre-stress, as well as the location of our tendon, right? So maksudnya dia sama je macam kalau RC design dah sampai dekat deflection check, whatever adjustments that we have already done, at this stage, will be carried forward to the next stage, right? So maksudnya untuk calculation yang seterusnya pun kita akan pakai value yang sama lah, right? So value yang baru lah, maksudnya instead of using 700, so sekarang kita akan proceed dengan 600 kilonewton with the eccentricity of 70 millimeters. Right? So faham maksudnya kita boleh buat dia punya adjustment lah. Tidaklah rigid. Kata kita dah pilih 700, lepas tu memang kena forever 700. Kalau tak kena redesign back all over again. No. Right? So the reason why we have this deflection check is for us to verify whether the selected values that we have already decided during kita punya Magna punya calculation tu betul maksudnya valid ke tidak untuk kita proceed with the calculation. Okay? Boleh? Right, so any questions with regards to today's lesson?
No, madam.
Right,
No,
so
madam.
yang mana yang you dah calculate untuk P0 ni, untuk P0 pula, untuk deflection ni, then nanti boleh masukkan dalam formative assessment untuk this week lah, formative assessment for week 7. Nanti saya akan create dia punya ni lah, dia punya tab tu untuk you masukkan di situ, right? Okay, so that you can keep your calculation yang mana yang you dah buat tu, then you can keep inside the formative assessment punya file lah. Jadi tak adalah hilang. Jadi maksudnya boleh tengok balik yang mana that you have already recalculated. Okay, right. So nanti saya akan bagi some questions, okay, with regards to the pre-stress loss, okay, dan juga some questions on this deflection as well, right. So nanti saya akan bagi together, then your calculation pun nanti boleh masukkan kat situ. Okay, right. So rasanya kita stop di sini, right. So next week nanti kita akan tengok pula untuk another one, okay, which is under serviceability limit state. Okay, so yang ni kita akan tengok sikit lah on the crack control. Okay, then the next one is on the flexural resistance, right. So bila flexural resistance ni dia adalah already under the ultimate limit state. Right, so yang ni adalah kita dah tak tengok dekat serviceability, so we are going to move on to the ultimate limit state. So we are going to do this next week lah. Okay, right. So yang tu adalah flexural resistance. Okay, then another week, okay, kita akan tengok pula in terms of shear resistance, right. Okay, so yang these two falls under the ultimate limit state, right. So saya dah masukkan notes dah, right. So if you want to download, okay, then you can download directly from your class notebook. So nanti saya akan masukkan juga dekat Teams punya files, okay. Right, so kalau tak ada apa-apa rasanya kita stop di sini, right. So insyaAllah we will meet again next week, right. So on Tuesday, right. So Tuesday online class, Thursday kita buat face to face lah insyaAllah. So kalau kata ada any discussions, okay, that we can do right before our test, right. So because our test will be on next Friday, right. So sempatlah kita jumpa Khamis tu just in case you have anything to ask, right. So as for the coverage, okay, for the test, right. So kalau tak silap saya kita sampai cable zone profile sahaja. Right, so nanti kejap saya tengok dekat lesson plan. Then pasal dia sepatutnya only sampai week 7. Kejap, pasal sepatutnya test is okay, dia sepatutnya masuk sampai week 6 lah. So the furthest pun kita akan pergi sampai pre-stress loss, right. So what we have learned today ni tak masuk dalam test 1 lah. Okay. Right, so jangan lupa kita punya test next week, right. So nanti insyaAllah nanti kita in case you have anything to ask, right, so then boleh inform saya lah, right, so that we can discuss. Okay, right, so rasanya kita stop dekat sini. Let's end our class with tasbih kifarah and suratul Nas. Alright. Okay,
Thank you,
thank you
madam.
very much everyone. Jangan lupa tick attendance dekat YouFuture. Okay?
Okay, madam.
Thank you,
Thank you,
Alright.
madam.
Okay, welcome.
Thank you, madam. Thank you, madam.
Okay, Assalamualaikum.
Terima kasih, madam.
Alright,
Waalaikumsalam.
welcome.